Hello, AP Calculus, and welcome to today's asynchronous video filmed over the summer by Miss Bowman. Another rambling, a lot of pause, unpause. If you've never listened to one of my asynchronous videos, I'm going to be telling you to pause a lot, to try problems on your own, and to unpause me. This is the day 3 notes in entirety. Take breaks as you need. I wish I could, but I'm going to go through and just record this as fast as possible so that I don't talk too much. Okay, so today's lesson, we're going to be doing the day 3 notes, which are our main goal today. Well, we have 3 objectives. We're going to be able to, by the end of this lesson, determine if the derivative at a given a value exists, which we did talk about a little bit in lesson 2. And we're just going to kind of add on to that today, especially dealing with it graphically. You're going to be able to use the calculator and other devices to be able to calculate what we call numerical derivatives. And I'll talk a little bit about what that word numerical means when we get there. And then thirdly, because calculus is based off of all the representations of functions, numerical, graphical, algebraic, and verbal, meaning stories, today we're also going to spend some time interpreting the meaning of the derivative in the context of a situation. So if I give you a situation and tell you a derivative value, could you tell me what that means for that situation? Okay, so jumping right into differentiability, let's go through what we talked about last class about what it means for something to be differentiable. So just to recall, a function, and I'm going to use this shortcut for the word function all the time because I don't want to have to write the whole word. So just so you know, that's my little shortcut, Miss Bowman's way of writing function. A function is said to be differentiable if the slope from the left is the same as the slope coming from the right. That's going to ensure that the limit exists. And since the derivative is technically a limit, that's the only way it could exist. Okay. We say that f prime of a fails to exist where the limit fails to exist. Okay. So if we can't find the slope from the left and the slope from the right being the same, then that limit doesn't exist and that function is non-differentiable. So there's differentiable places in a graph and non-differentiable places in the graph. Just like there are continuous places and discontinuous places, the same thing here also applies. So today we're going to kind of focus on graphically, how can I tell where a place is non-differentiable? The places where functions are differentiable are about 99% of the domain. Okay, so if you're looking at a graph, all the points on that graph are usually differentiable. There are a few exceptions to where a function can be differentiable, and we're going to talk about those. And they kind of fall into 4 categories, although one is a little misleading. Okay, so places where a function is non-differentiable. The first type of non-differentiable place are discontinuities. Continuity is a necessary condition for differentiability. So if a function is discontinuous or is not continuous at x equals a, then the function is automatically not differentiable at x equals a. So just to kind of recall, take maybe 20 seconds and pause me. Think about the types of discontinuities we've learned. Okay, unpause me when you're ready, and we'll go through them. So the types of discontinuities we can have are jumps. We could have holes, which are the removable kind. We could have what we call infinite discontinuities, which are your asymptotes. And the third or the fourth type, because I can count 1, 2, 3, 4, was those oscillating discontinuities. Those are those ones that go, hi, I'm oscillating too fast, WTF, I don't know what's happening. Okay, so those oscillating discontinuities. So any place that is discontinuous is automatically not differentiable. So that's nice for us. So if we see a discontinuity, we're like, bam, if there's an asymptote at x equals 1, that means x equals 1 is not continuous and it's not differentiable. Now, differentiability, if I told you a function is differentiable, I automatically know it has to be continuous because that's a condition that's necessary But just because a function is continuous doesn't always mean it's differentiable. So there are 3 exceptions to a function being continuous but not differentiable. And they are the following. The first type is called a corner. A corner is where the one-sided derivatives are different. By definition, the slope from the left. So I'm just going to say left m doesn't equal right m. The most common one that you would see would be an absolute value graph. So if I look at an absolute value graph, okay, the slope from the left on the left side of x equals 0 is -1, and the slope on the right side of x equals 0 is 1. So this point right here where the two slopes meet, that place is a not differentiable place. Now, is the function continuous there? Yes, it's got a point, x at 0, 0. It's got a limit because the two functions are approaching the same height, and the limit and the point are the same. So that place is continuous, but it is not differentiable. So anytime we have a weird, like sharp turn on a graph like that, that's going to be a place where the function is continuous, but not differentiable. It's called a corner. Now, the next type of continuous but not differentiable, okay, is going to be where the slope approaches infinity. Not where the function approaches infinity, but where the slope approaches infinity. So what would that look like on a graph? Okay. On a graph, it would look like this. Now I got to change colors again. Here I am. And then it gets really vertical and then continues on. This place right here, the slope is, the tangent line would be a vertical line there, and vertical lines have undefined slopes. So this slope is a positive infinity. It's all rise and no run. This is called a vertical tangent. And it's because if I were to draw the tangent line, it would be a vertical line, which has an undefined slope. Therefore, undefined slope means undefined derivative. Okay, so that's a vertical tangent. And just so you guys know, this graph right here is y equals the cube root of x. So just in case you want to see like an actual function that looks like that, that's what it would be. Okay, the last type, this is the one that confuses many people because a cusp is a special corner, okay? So if you call something a cusp that is not a cusp, that is the biggest mistake people make. Special, there we go, corner. Okay. Cusp is to corner as square is to rectangle. A cusp is a specific type of corner. And it is what I would like to say is if vertical tangents and corners got together and made a baby, then that would be a cusp. So what do I mean by that? Well, the definition of a corner is that the left slope and the right slope aren't the same. Okay, so we know that much. The definition of vertical tangent is where the slope approaches infinity. So the definition of a cusp is where the slopes aren't the same and at least one of the slopes is approaching infinity. So we can say slope's not equal, and at least, I should have just used the symbol, at least one slope. Wow, my poor little laptop, guys. At least one slope equals plus or minus infinity. Okay, so here's what a cusp would look like. I'll make some axes. If I had a graph that looked like this and then went off, that is a cusp. Now, if you said corner, guys, you would never be wrong. So saying something, that's like calling a square a rectangle. Is a square a rectangle? Yes, technically it is. You are not mathematically inaccurate. What makes this corner a cusp is the fact that coming from the left, do you see how the left slope is approaching a vertical, like very, 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 very steep slope, whereas the right slope is something different? That's what makes this corner a cusp. Okay, so that's one instance. I could also have something that looks like a bird that you would have drawn in like third grade. So if you remember like third grade birds, you kind of drew them like this. That is also a cusp. Now, coming from the left, it looks steep, and coming from the right, it looks steep. But if I look at the two vertical tangents on each side, one is decreasing, so it's negative. The other is increasing, it's positive. They're both infinity slopes, but they are different infinities. This slope coming from the left would be negative infinity, and the slope coming from the right would be positive infinity. Okay, so because they are different, it's technically a corner, and because one of them, at least one of them, is an infinity slope, it's called a cusp. So those are the three types of places where a function is continuous but not differentiable. So if I ask you to look at a graph and be like, where is this function continuous? For instance, this absolute value. Let's look at this one right here. Where is this function continuous? I would say from negative infinity to infinity. Where is this function differentiable? Well, I would say negative infinity to 0, 0 to infinity. It's differentiable everywhere except that corner, okay? Another way you can tell if a function is going to be differentiable is to think if it's differentiable, it has a slope. If it has a slope, that means there has to be a tangent line. So differentiable functions have a property called local linearity. And all local linearity says is that if I were to graph something that's differentiable, and I were to focus on one part, so I'm going to take a picture of one part of this graph, maybe. We'll see if she wants me to do it. There she goes. Maybe. Just kidding. Oh, there she is. Okay, so I'm going to take a picture of one part of this graph, which is a parabola. It's definitely curved. Now, what makes it differentiable, another way you can tell, is if I zoom real close into this function and I look at that place, it's starting to look more and more linear. In fact, if I were to draw the tangent line on top, the tangent line and the actual line, although this is like really thick, the tangent line and the actual line don't really have much difference. I mean, they do at the edges, but like right here in the middle, they're basically the same. We say that that function is locally linear because if I zoomed in to a local spot, it looks like a line, which means it would have a tangent line, have a slope, and be differentiable. Okay, in the jargon of like graphing calculators, differentiable curves will like straighten out if we zoom on in them if the point is differentiable. But for instance, if a point is not differentiable, like in our absolute value graph, no matter how far I zoom into the vertex of absolute value, so if I have an absolute value graph, and let's say I want to take a picture of the place that's not differentiable. So I'm going to localize, if you will. Maybe, maybe not. Doesn't really like my camera today. Well, imagine if I were to localize and zoom in here, even if I blew that up and got closer, it's still going to look like an absolute value. It'll never look like a perfectly straight line, no matter how close I get. That's a place that's not differentiable. Okay, so here's what I want you to do. On the next page, there are 8 graphs. So I want you to pause me, and for each indicated X value on one of these graphs, I want you to indicate, is the function continuous at that point? Is the function differentiable at that point? Is it both or is it neither? Okay, so is it continuous but not differentiable? Is it differentiable but not continuous? Is it both? Is it neither? Okay, I'll give you one hint. One of those things I said is not possible. Okay, so pause me, try these. Both, neither, continuous, not differentiable, differentiable, not continuous. Okay, I'll give you a second to pause. Okay, welcome back. Let's go over them real quick. So looking at x equals 3, is the function continuous? No. That automatically means, is the function differentiable? No. So this one would be neither. Okay, the second one, is the function continuous at 1? No, which means it has to be neither, because a function cannot be differentiable without being continuous first. Okay, looking at x equals 0 here. Is it continuous? Yes, no holes, jumps, or asymptotes. Is it differentiable? Well, I'd have to look. Is this a corner? No. Is it a vertical tangent? Nope. It's a horizontal tangent. The slope there is 0. So this would be both continuous and differentiable. Okay. For D, if I look at x equals 0, is it continuous? Yep, I can draw the whole thing without lifting a pencil. Is it differentiable at x equals 0? No. So this one would be, I'm just going to say C, not D. So this one is continuous, but not differentiable. Okay, at 2, this is supposed to be an asymptote. You just can't see. So this is neither because it's not continuous. Here at x equals 0, this one is continuous, but not differentiable. This one, and if the reason why would be there's a corner. Here, this one is continuous, not differentiable. Now, a lot of people are like, oh, Ms. Bowman, isn't that a cusp? No, this is a corner because this is like a slope of 1/2 or whatever. And as I'm going here, it's flattening out to a slope of 0. Neither of those sides are getting completely vertical. That's just a corner. A cusp has to be approaching an infinity slope. Speaking of which, if we look at H at -1, is it continuous? Absolutely. Is it differentiable? No. And why not? Because it has a vertical tangent. Okay, so if I look here, this is what we call a vertical tangent. So that is a place where the graph, this tangent line would be a vertical line, which has an undefined slope. Okay, so that's kind of our talk on differentiability. Somehow when I'm always filming these, I get like the worst coughs, and I don't cough like this at any other time in my life. All right, next I'm going to show you the graphing calculator trick. Your calculator will do derivative values for you. It won't do like the general derivative, but it will give you like the slope at a point. Okay, if you have an 84, it's going to look slightly different because all I had was an 83, and they've upgraded the operating system and it looks a little better. Okay, derivatives calculators can technically do what we call numerical derivatives. So what do I mean by a numerical derivative? Well, a numerical derivative is just an approximation. So this is using an approximation of IROC. Okay, it's not taking a limit, guys. The calculator does not know what a limit is. It does not know how to take it. What it's doing is what you did in Math 3. Okay, it's taking, like if I want x equals 2, it's going to take the slope between 1.9999999 and 2.0000001. Okay, so it's finding the slope right around 2. And why does that work? Well, if the function is differentiable, it's locally linear. So as long as I stay really close, you're not going to be able to tell the difference between the tangent line and the actual point. So the slopes are going to be basically the same. Okay. The calculators will lie to you, and I'll talk a little bit about that after we try a problem. So we're going to try a problem. So if you are trying to do a calculator, grab your calculator. Pause me if you don't have your calculator because you're going to need it. Okay. Pause me, grab your calculator, and then unpause me, and we'll continue. So now that you have your calculator, if you look at the commands, there is a math command here. Now, some of you can do these shortcuts like the F1, F2, F3. I also think it's under either F2 or F3. But regardless, if you go to math, which is this menu, and you scroll down to number 8, you are going to see the following phrase, NDeriv. What does that stand for? Numerical derivative. Okay. Now, depending on what type of calculator you have, it's going to be a little bit different of a screen. So let's do an example. We're going to do f of x equals x squared plus 3 at x equals 2. Now, if you have an 83, when you select number 8, you're going to get a menu that looks like, I need a new page real fast. Okay, you're going to get a menu that looks like this, NDeriv, and then it opens parentheses, okay? If you have the 84 with the new operating system, you're going to get something that looks like this. Okay. Notice this notation, it's talking about the command. So if you have the bottom notation, you're going to put the x here, and you can use the x variable button to type it in real fast. You're going to type your function, x squared plus 3 here, and x equals 2, because that's where we want the slope at. If you have an 83 or an older one, you're going to have to type the function, then a comma, x. So it's basically these same three things, except we're doing the function first, then the x, comma, then the value. Okay. So go ahead and try that, and you'll see when you get that and hit equals, you get a slope of 4. So f prime of 2 is equal to 4. Okay. I think that's about it, and I have it here if you want to see it typed in. That's how it looks. Now, those of you that have the older operating system, if you want to know where the comma is, it's right above the 7. So that's the little comma button. So you would just type x squared plus 3, comma, x, comma 2, and then close your parentheses. Okay, if you are using things like Desmos, Desmos will also do the derivative value for you. If you're comfortable with it, you would just have to put f of x equals x squared plus 3 in the first line of Desmos. Okay, just like that. And then in the second line, do f prime of 2, and the answer should appear like down here. It'll say 4. Okay, so practice with both, get comfortable with both. There are going to be times where I'm going to ask you to do it in the calculator. There are going to be times I'm going to ask you to do it by hand. Okay, the warning thing, because the calculator is stupid, okay, and it's taking 2 points around a function to find the slope. If you have a place that's non-differentiable, it's not going to tell you DNE, which is what it should tell you. It's going to give you a number. So for instance, if I have the absolute value graph and I want to find the slope, and you found like the derivative of absolute value of x at x equals 0, it's going to tell you the slope is 0. But you know, looking at it, that there is a corner here. That's because the calculator is taking the 2 points right around 0 and finding the slope between those 2 points. And the slope between those 2 points does exist. It would be a slope of 0, but the slope at that corner does not exist. So just be careful, because it is not as smart as you think. Okay, and that's the calculator. So 2 objectives down, 1 to go. So now what we're going to do is we're going to practice interpreting the derivative. A big thing with calculus and a big revolution has been in the IMP spirit that everything should be within the context of situations. So in math, we model situations with expressions and functions to like find stuff out about a situation. And then we have to like interpret our results. Okay. So we're going to practice interpreting what the derivative means for a given function. So I'm going to do the first one, and then I'm going to ask you to pause me and try number 2, 3, 4, 5. And then we will go through, I'll go through the answers for each one. And if you have questions, again, please feel free to email me, put it in the group chat, or come to office hours. Yeah. Okay. So suppose S equals f of t. So all this is saying, guys, in math jargon is saying the function's name is S and it's a function of time. So that's really all that means. I'm feeling purple. Actually, you know what? I'm going to get a little fancy. I might use a little calligraphy pen. Okay, so this is just telling me that it's a function of time and that the function's name is S. And it says, suppose that S gives the distance in meters of a body as a fixed point as a function of time in seconds. So if I said S of 3 equals 10, you would interpret that as at 3 seconds, the distance is 10 meters, okay? So a function is going to measure the distance. And I always want to make sure I mention like what the input was. So 3, in this case, seconds. The distance is 10, output is meters, okay? So that's what be with the function. So the function tells me what something is. The derivative is the slope, which means it's the rate of change. So what information do we know if ds dt? So pay attention to this. This is the Leibniz notation. This is just saying the change in s with respect to time. This is just the same thing as s prime. Okay, so ds dt at t equals 2. That's one thing that we're going to talk about is if I wanted to say s prime of 2, I would write it like this. But with Leibniz notation, you would say ds dt such that t equals 2 is. Okay, so they're telling us that s prime of 2 is 10, or that ds dt at t equals 2 is 10. So that's the slope. So if I want to like interpret the meaning of this, the function gives me what something is. The derivative tells me how it's changing because it's a rate of change. So we're going to say at 2 seconds. Okay, and usually if you start it like this every time, you're going to get full credit. Interpretations and explaining the meaning and the context of a situation are always questions on the AP free responses, and they're always going to be worth points. So these are like a sentence stem that you can kind of figure out how to get the points every time. So at 2 seconds, the distance, because that's my function, is changing at a rate of 10, and then this is important. If it's the rate of change, this is why Leibniz notation helps me. S is meters, T is seconds, so I know this has to be meters per second. Okay, so at 2 seconds, the distance is changing at a rate of 10 meters per second. There we go. That's our answer, and we have gotten full credit in interpreting the meaning. Now, there are a couple of different ways that you could have said this. You could have said this at 2 seconds, the distance is increasing at a rate of 10 meters per second. Okay, you could say that the rate of the distance is 10 meters per second. What you can't say is that the rate is changing, because that would mean something completely different. Okay, and then the only other thing is if this was a negative 10, that would tell me that the distance is decreasing because the slope is negative. But I'm not going to say decreasing at negative 10. I'm going to say decreasing at 10, because the word decreasing already infers the negative. So don't ever use a double negative. Don't do decreasing at negative. Either say changing at negative 10 or say decreasing at 10. Okay, but don't say decreasing at negative 10. That makes literally no sense. Okay, so try the rest of these. Okay, of 2, 3, 4, 5. Pause me, try them, and then we'll go over it, and then we'll be done for the day. So pause me, take a few minutes, try it, unpause me while I take a sip of water. Okay, welcome back. Now that you've tried these questions, the cost seat in dollars. So I always like to underline when I'm reading, because that just like annotation helps me. The cost seat in dollars of building a house A square feet in area is given by the function C equals F of A. So I know C is the output and A is the input. What is the practical interpretation of F prime of A? So this is going to say at A square feet. I don't like the way this is looking, because it's, well, that just looks weird. At A square feet, okay. The cost is, the cost is changing at, man, this is not looking like English. Changing at a given dollar per square foot. Oh man, my life. I tell you what, guys. Okay, so the important part is that the derivative is talking about how the cost is changing, okay? And the units of the derivative would be dollars per square foot. It's always going to be a fraction because it's slope. It's like a change in y over change in x. Okay, let's look at the next few. So the cost of extracting T tons of ore from a copper mine is C equals F of T. So C is the output, T is the input. The cost is in dollars. What does it mean to say that F prime of 2,000 equals 100? So if I look at the input, I know that's my tons. So I'm going to say at 2,000 tons, at that moment, the cost is changing at a rate of, in this case, I'm going to switch it up and say increasing at a rate of 100. And then my units, C is cost measured in dollars, so it's going to be dollars per, my T is ton, so dollars per ton. And that's all really, this is like the way to do it every single time and get full credit. Okay, so if Q equals F of P, so I know P is the at part, Q is the function, gives the number of pounds of sugar produced when the price per pound is $3. Okay, what are the units and the meaning of the statement f prime of 3? So at 3, now 3 is my P, it's going to be at $3 per pound because it's the price per pound. The number of pounds of sugar, because that's my function, is increasing at 50 pounds per dollar per pound. Now you're like, those units don't make a lot of sense. But it's because it's not $3 that they're spending, right? It's $3 per pound. So it's not going to be like $50, 50 pounds for each dollar. It's like 50 pounds for each dollar per pound. So it's actually going to be like $50 because it's dollar per pound. Anyway, okay, so if you're ever confused, just follow that it's the output over the input, and that kind of gets you through it. Now, this last one you might have gotten a little tripped up because I threw some little math for in review. Suppose P equals F of T is the population of Mexico in millions, where T is the number of years since 1980. Explain the meaning. So T, this is P. So at 1986, or you can say 6 years after 1980, or I'm going to say in 1986 because at 1986 doesn't make sense for this. F prime. So the population. Now, if it was F, it would be what the population is. If it's F prime, the population is changing. So I'm going to say increasing because it's positive at 2 million per year. Okay. Now look at this one. This notation is something different. This notation is the inverse function. So if you remember from Math 4, inverse functions are where the domain and range are switched. So if this is time and this is population in the regular function, then in the inverse function, this is population and this is time. So if this is just a regular function, notice there's no prime notation. This is just what the function is. This is saying at a population of 95.5 million, the year is 1996. Okay. Or you can say when the population gets to be 95.5 million, the year is 1996. Okay, but it's at the input, which is years, the output is input is population, the output is the time. Now this one has the inverse and the prime, so this is going to be a rate. So we're going to say when the population, or at the population, I'm going to say when because it makes a little more grammatical sense, when the population of Mexico is 95.5 million, okay, the time is increasing at 0.46. 0.46. Let's try to write a 6. That's kind of a 6. All right. I got to erase that. Okay. At 0.46 years per million person. Now, a lot of you want to write million people per years, but this is the inverse. So this is saying every time we increase by 1 million people, the years are increasing by 0.46 of a year. So like, what is that? Like 5 months or so. So every 1 million people that have grown in Mexico, the time has increased by 5 months, if that makes sense. So it's years per million people. It's like the same thing as saying I'm getting 5 bananas for $1, or each banana costs 20 cents. It's that same idea. I just wish my computer would write the word people so it didn't look like chicken scratch, but it is what it is. You heard me say it. Okay, so you have some practice with the interpreting the derivatives. Again, let me know if you have questions, but otherwise, have a great day and I will see you soon.